So I'm Eske from Aarhus University, and I've been looking at how to formalize decentralized exchanges and similar kind of smart contracts inside of CoC, together with Danil, Annenkov, and Dexter. So you probably all know what a centralized exchange is. You use it every day, like your bank when you use your credit card in a store. But centralized exchanges can give many problems. Many of you have probably heard of FTX and probably know how bad that went. So I probably don't need to say much more about why it's a bad idea. Luckily, there is some proposed solutions to this, decentralized exchanges. And when we are talking about blockchain, it's of course obvious why weren't the exchanges already decentralized? Because that's the main selling point of blockchain is decentralization. Luckily, we can decentralize exchanges on blockchain using smart contracts. The problem is that smart contracts are really hard to get right. So there was this analysis last year that more than $3 billion was stolen due to decentralized finance thefts in 2021. And this number is just expected to grow. And there are plenty of examples of smart contracts having huge financial losses because of flaws in them. So for those of you that don't know what a smart contract is, a smart contract is essentially a piece of code that you attach to some address on a blockchain, and whenever someone sends a transaction to that address, the code will get invoked. It will take its current state, do some computation, output a new state, and a set of transactions such as transferring money to some specific person or calling another smart contract, or even calling itself. So smart contracts are hard to protect. First of all, because they're very open, so it's very easy for adversaries to analyze and find vulnerabilities and very easy for them to exploit them. But it's also very hard to protect because once you deploy a smart contract, you can't change the code. The code is just a contract, it's the law. Once it's there, you can't change it. So obviously, it's very important to get smart contracts right before you deploy them. So our contribution is that we verify one specific decentralized exchange called Dexter. Though the methodology we use is not specific to Dexter, so you could use it for any similar decentralized exchange or just similar smart contract. And then what is really interesting is that we prove properties about interacting smart contracts, which is something that other frameworks in the area are not really capable of. And these improvements and this work, we contribute to the Concert framework. So Concert is blockchain and smart contract formalization inside of CoC. It's a framework that is meant for both developing, testing, and verifying smart contracts. So it's supposed to, at least the end goal is that it's supposed to help the developer throughout the entire process of developing a smart contract. So it's all inside of CoC. It has a formalized execution layer and also has an executable implementation of the blockchain, which means that you can actually execute your smart contract inside of CoC, which allows us to do things like property-based testing using the quick check framework. Similarly, we make use of the verified erasure in MetaCoC to provide verified extraction to several different smart contract languages. And this is all out there already, previous publications. So in this work, we make use of this to sort of extend it and look at how you can say something about interacting smart contracts. So in Concert, a smart contract is simply about just a pure CoC function that transforms state. It's implemented by just two simple functions, an init function and a receive function that takes a state and outputs a new state at some transactions. And the execution of this is formalized by some scheduler, which is basically the entire execution model. So it handles updating blockchain state and executing calls and all of this. And all of the execution is captured in traces, which allows us to actually prove very interesting properties because we have the full execution trace. And there's also a small steps arrays and semantics, which you can see here. That's not very important for this talk, but it's there. So Dexter 2 is a decentralized exchange And being a decentralized exchange, it means that there's no third parties involved in exchange transactions. There's no central point of failure besides the smart contract, of course. As the name suggests, it's a complete rewrite of Dexter 1, which was found to be very insecure. And since it's an exchange, it allows people to trade 2 different cryptocurrencies on-chain. And it's really interesting, Dexter 2, because Dexter 2 was actually chosen to be part of the native Tezos blockchain protocol. So it's actually supported directly by the blockchain. It's so roughly 600 lines of CameLIGO code, which is camel-like language for blockchains. And it's basically implemented by 3 main contracts. So there's the token contract, which is the contract which holds tokens that you want to trade. There's the CPP' contract, which is the main contract, which is the one that actually implements the market. And then there's a liquidity contract, which is responsible for managing ownership of the liquidity pools. Because since it's a decentralized exchange, there isn't as one single provider of liquidity. And instead, users are incentivized to provide this liquidity in return of some promised investment. And as you can already see, so there are 3 contracts, and these interact in different ways, and the user can interact with all of them. So there's already some complex interaction patterns here, but it gets even more complex because a single instantiation of Dexter 2 can communicate with any other instantiation of Dexter 2 available on the blockchain, even those that are deployed later. And even more, the token contract can communicate with any number of unknown smart contracts if it wanted to. And these smart contracts could then call back to the main contract, and you can get sort of crazy execution traces and loops. So in this work, we mainly focus on the main contract and the liquidity contract, because the token contract there isn't one specific token contract. The exchange is designed to work with any token contract, and there are hundreds of token contracts, so there's little to no gain in verifying it with a single token contract. So instead, we find some properties that the token contract has to have for it to be secure. So the general process is that we take the unverified LIGO smart contracts and some informal specification provided by the developers. We then translate that to a COG smart contract and functional specification like IO specification, and some higher level properties. And these higher level properties are where the main work is and the most interesting ones, because you really need the execution traces to say anything about those, and many of the very complex flaws that you find in smart contracts are due to things like reentrancy, which you can't capture with just simple IO input-output specifications. We then can put this specification into the project-based testing framework and get tests, so we can stop wasting time proving things that obviously aren't true, and then after that continue to actually building proofs. And similarly, we use the verified extraction to get a verified legal implementation of the smart contract. In total, this, once ported, is about 1,000 lines of code for the smart contract, and proof and specification is about 3,500 lines of code. During just proving the specification, like the input-output specification, we found several inconsistencies between the specification and the reference implementations. Luckily, all of the inconsistencies were problems with the specification and not problems with the code. So as I mentioned, really the main interesting thing is the interaction between these smart contracts, because that's where a lot of things can go wrong, and it's sort of the hardest thing to reason about. So one property that is very important for Dexter 2 is that we have these 3 different contracts. Each of them hold a different type of assets. So the token contract holds tokens, which we denote by T. The main contract holds the native coin that with the other type of asset you want to trade, which we denote by X. And the liquidity contract holds some liquidity token, which represents ownership of the liquidity pool, denoted by L. And to produce, since this is a decentralized exchange, there are no third parties. So the contract has to figure out fair exchange rates by itself. And to find these fair exchange rates, it has to know all these three variables. The main contract has to know all these three variables. However, calling between the contracts can be insecure and slow. So instead, the main contract keeps a tally of how much it thinks each of these have. And you can probably see where I'm going right now. So we have an actual amount, and we have some view of what the actual amount should be. So these should, of course, be equal. But this, of course, requires that we can reason about the interaction of the smart contracts, because they're not updated at the same time, and that they live in different smart contracts. So we get some kind of theorem saying something like, for any reachable state of the blockchain, L should be equal to L prime. And these are parts of two different, so L lives in the state of one contract and L prime lives in the state of another contract. Now, normally you would prove some kind of invariant like this in concept by doing induction over the trace. And we could certainly try to do that. And concept even comes with a very nice induction principle for doing induction over the trace. The problem is that that only works for single contracts. And here we have an invariant with multiple contracts. So we could try to sort of make a new induction principle that works for two smart contracts. But then you have a problem. What if we have 3 smart contracts? What if we have 4 smart contracts? How many induction principles do we want to maintain? Like, this is, of course, not feasible. So what we wanted to do was find something more modular that would scale well for communication between any number of smart contracts. So by doing this the hard way, we sort of found that there are really 3 parts that you care about in such proofs, which are some kind of computation that updates the state in one contract, some kind of computation that updates the state in another contract, and then you have the communication. Like, those are really 3 separate parts that you want, and what you really want to talk about is the communication, but what this lemma really says something about is the state. So what we did was, when we came up with this approach where you sort of find some relation between the state and the message is received and the message is sent in one contract, and some relation about the other state and the message that sends and receives. And now we have 2 completely different properties that are both single contract invariants, so those can be proved using the existing infrastructure. And then we can use those proofs to sort of erase the state completely from the main theorem that we wanted to prove, reducing it to only talking about the communication, which is the actual part that we care about. Thus, we get a more compositional way of proving this, which scales well with any number of contracts and also makes it more modular, smaller proofs. Of course, there are many other proofs. We didn't only prove that theorem, but there are way too many to mention. In total, the formalization is about 5,500 lines of code. And it shows that we can really have a fairly modular approach to verifying even very complex smart contract interactions with many different smart contracts. Thank you.
Thank you. And any questions? Oh.
Well, can you explain a little bit more on how you compose the proof for a single contract to get the proof for the whole system?
Yeah, so the idea is that you specify the relation between the state and the messages sent. And once you sort of have that relation, so that relation between the state and the messages sent, that's only something that the contract A knows, right? Whereas the other one is only something that contract B knows. So those are sort of you sort of have one thing that's only about contract A and one thing that's only about contract B. So they can obviously be proven using the existing infrastructure. But now you have something that relates L to the messages sent. So you use that to eliminate, you use that relation to eliminate the state of contract A in the main theorem, such that now you only have something that relates to the messages sent, if that makes sense. And the nice thing is that if you reduce it to talking about only the messages, then you are left with just the communication, which is the tricky part. And you can also you can prove a lot of general theorems about how this communication works for arbitrary contracts. So you can sort of reuse a lot of code, a lot of proofs.
Okay. So, any other questions? Then maybe I can ask my question. So, as far as I know, there are various kinds of consensus protocols out there, like hot stuff or PBFT and many more things to support blockchains. So, how do you relate your work with them? Like, is your work able to? I mean, can your work be composed to those other consensus protocols?
So the consensual protocol really has nothing to do with the execution of smart contracts. It's completely separate. So the consensus protocol is, we don't even formalize that because it doesn't influence smart contract execution. So I think what you might think is about different execution models where, for example, that's the Ethereum model where we have something that sort of looks like direct calls, but aren't actually direct calls inside of smart contract, where we have something like the Tezos model, which is the one we are in, where you have message passing.
Okay, but doesn't the smart contract, I mean, isn't it built on consensus protocols? No.
So the consensus protocol only determines how things get onto the block. We don't really care how things get onto the block because we just care about what, once it's onto the block, it gets executed correctly. So the consensus protocol is only for how and what gets on the block.
Okay. So let's thank again speaker.